Hi, I'm Dr. Justin Esarey, and what I want to talk to you about today is the role that assumptions play, model assumptions specifically play, in the generation of statistical results and inferences. And I'm going to start off by talking about the most basic problem that any researcher faces, which is upon confronting a data set like this one I'm showing here on the screen, what do you do with it? How do you use it to do things that you'd like to do? So what I've got here on the screen is it's a fake data set that I've made up. The y-axis has hypothetical incomes in US dollars, so annual incomes, one presumes. And on the x-axis, I've got education levels on an ordinal scale from 0 to 7, where higher numbers indicate greater education. So this could be something like 0 stands for less than grade school or did not finish grade school. 1 is finished grade school. 2 is finished, or some high school. 3 is high school. 4 is some college. 5 is college. 6 is some postgraduate, and 7 is some postgraduate, and then 7 is finished a postgraduate degree, a master's or PhD, something like that. This is just a sort of basic data analysis that one might easily encounter in a data set like the GSS or maybe the World Value Survey. And so what we want to do is say something about the relationship between income and education. We want to, in a word, we either want to test some kind of hypothesis that we have about the relationship between education and income. Usually this is along the way of testing a theory that generated that hypothesis. And I'm going to be somewhat agnostic about precisely how hypothesis testing relates to quantitative analysis. At least for this particular lecture, it's a very deep topic, and one that I don't want to spend a lot of time on today. Suffice to say, though, we could use the data toward this purpose. In order to do so, we'd have to develop a model, which is really what I want to talk about. Another thing you might want to do is predict future observations. So we might want to do this for a variety of different reasons. We might have a policy initiative that we're interested in. Whoops. Policy initiative. So we might want to, for example, figure out what we would expect to happen for individual incomes if we increase the level of education in a community via some kind of intervention. We might be interested in just forecasting, pure and simple. We might, for example, be interested in what is the state of the economy at the individual level going to look like in 50 years, given some trends we have on education. We might also be looking to validate a model. So we might be looking to create a statistical model using an existing data set and then see how good that model is at predicting data that was not used for the model's creation. For any of these reasons, we might be interested in predicting future observations. So hypothesis testing and prediction are two things one might conceivably do with a data set. And in order to do that, we've got to generate a statistical model that will give us future predictions and allow us to detect relationships that we would find either consistent or inconsistent with some theoretical hypothesis. And so when one looks at a data set like this one I've shown you here, the real point that's important to remember is that the inferences that one makes, so inferences and predictions that one makes, are only as good as not only the data that went into generating those inferences and predictions, but the assumptions that were made to build the model out of which those inferences or predictions came. And the relative content of a statistical model can be different in terms of how much on balance it relies on data or assumptions, to make some kind of claim. So, in other words, some models are assumption laden, have lots of model assumptions, and some are less assumption laden. They let the data speak for themselves, so to speak. So this raises a sort of a question. Why would anyone ever want to use anything but the lowest assumption models? For example, a linear model is a very assumption-laden model. If you think about what a linear model does, and you can draw a little graph here and sort of get a sense of, well, here's some data I've got. If one runs a linear model on data, you're making a pretty strong assumption about what the relationship between those two variables is. You're specifically assuming that it's aligned, that the relationship takes the form y equals mx plus b plus some error component, or as we usually write in statistics, beta 0 plus beta 1 x plus the error term. So here's x, here's y on this graph. I'm making some pretty strong assumptions about that data by imposing this linear structure on it. And why would I do that? Why wouldn't I try to do something a little more flexible? Now, we probably can figure out that drawing a model like this, where we're just sort of connecting dots, is kind of not a good idea. There are lots of ways to show that that doesn't work very well. For example, if we do out-of-sample forecasting, the new data points appear for which we couldn't draw the line in between them, and so we typically get terrible predictions out of sample with that kind of extremely naive process. But maybe there's something in between linear models and this sort of connecting the dot style modeling where we could do better. And in particular, what I'm thinking of is there are obvious cases where a data set will not follow a linear format. So you might have data points that look something like this. And we look at that and say, well, that's probably not a linear model. Probably, if we were to try to draw a linear model on top of it, we would end up sort of over-predict or under-predicting a good bit of the data set and over-predicting other bits of the data set. In other words, we're trying to split a curve using a line, and we don't fit any points on that curve very well through that process. Maybe it would be better if we could, create some kind of model that, followed the trend of the data set a little more flexibly or more closely to get us better answers. That would be a good thing, one would think. Well, the point of this lecture is that there are good reasons to use the linear model, and those reasons are best illustrated by showing the results of using low assumption approaches on some sample data sets. So there are lots of low assumption approaches. Generally speaking, the family of non-parametric models embodies these low assumption approaches. Non-parametric simply meaning there are no formal mathematical structures imposed on the data that are flexible only through a discrete set of tunable parameters. So a parametric model is one where there is a structure, and the structure can be tweaked by tuning these parameters. A non-parametric model does not follow that structure. And there are innumerable non-parametric models. In fact, I've offered entire classes that cover that kind of material. I just want to focus on one example to give you a flavor of the strengths and weaknesses of using a low assumption approach. And that's the Nadaraya-Watson non-parametric estimator. The Nadaraya-Watson non-parametric estimator is a really simple conceptual procedure. Imagine you've got a variable y that you're trying to explain and a variable x that you're going to try to use to explain it. And you've got some data, like so, and you've got a point that you'd like to predict. So I want to predict, for this particular value of x right here, call it x0, I want to know what y I should expect there. Well, what the Nadaraya-Watson approach says is, in order to figure that out, let's just take a window of data nearby to x0. So we'll just create a little window of data here that we're going to examine. And we'll just take the average of y for all the data that's in this window, all the black points that are in this window. But we'll weight the ones that are closer to our target x value more heavily, and ones that are further away less heavily. And so what we'll do is we'll create a weighted average, and the weight will follow some kind of function, usually called a kernel function. And so we might, for example, impose the normal weighting function, where points that are really close to the target get really high weights like that, and points that are further away get lower weights according to this function. There are many alternative weighting functions. For example, there are Epashnikov functions that look more like this, a little more quadratic. There are uniform weighting functions where all the points are weighted equally. Lots of different choices, but all of them follow the same procedure of some kind of weighting. They're all just weights of some shape. And so our prediction for y at x0 is just going to be the weighted average of all the observed values of y. Whoops. Hold on. There we go. So all the observed values of y in the window times the kernel weighting function, which is a function of how close the x value of the point is to the target value. And then you divide by the sum of the weights just to make sure that this is truly an average, just like with any weighted average. That's the Nadaraya-Watson estimator for prediction. And it's a very simple and yet very flexible process. It's really good at picking up things, picking up localized changes in the data generating process. And for this particular DGP, a linear model, you can guess, would probably be quite bad. It probably would draw something like this, and you could see we'd be systematically under-predicting all these observations and over-predicting these observations. Whereas the Nadaraya-Watson model, if it's working properly, would tend to follow the structure of the model quite well. So why aren't we using this Nadaraya-Watson model all the time? Why isn't this something we do every day? Well, let's talk about some reasons for that. And these reasons are best demonstrated by just going to a data set. Now, here's a data set we have, and we created it, so it's, like I said, we know what it is. It's obviously linear. Nevertheless, I can use a Nadaraya-Watson smooth on it anyway. So what I'm going to do is I'm going to plot this data again with a Nadaraya-Watson smooth on it. And I get that smooth by using the lowest function, which is integrated into R. You can see I'm calling it here. And I'm running a lowest regression of income against education. It's a degree 0 estimate. Degree 0 means we're actually using the Nadaraya-Watson procedure. There are other more complicated procedures, such as local linear regression, that are classified as degree 1, or local quadratic, which are classified as degree 2, plus many other choices besides that one could use. And I'm specifying a span. I'm actually going to specify a span of 0.25. What this means is that I should use 25% of the data on either side of the target point. So for example, if I'm going to predict income for a person of education 4, I'm going to take a window around the data set that encompasses 25% of the total available data on either side of education 4. Now in this data set, that's going to be probably 3, 4, and 5. In other words, the points that are nearest to 3, 4, and 5. So that's this. I'm just running that lowest model. The predict function gives me predicted income values out of that model, and I'm predicting them for values of education from 0 to 7. In other words, all of the discrete values of the DV, and I don't want standard errors. In fact, the lowest function cannot give you standard errors out of a Nadaraya-Watson function for reasons I don't fully understand. So I do this prediction, and then I draw lines giving me the prediction, and bam, there's my Nadaraya-Watson smooth. Now, it's pretty darn good. I mean, it's pretty close to what the true line is. You know, because we created it, that the true line is an intercept of about 8,000 and that the slope is 10,000. Okay, so we're getting pretty close to that, although the intercept's not doing too well, I must say. Oh, these poor, sorry people down here have negative income. They must be in debt. So our Nadaraya-Watson model does all right, not too bad. But because we know that the model is linear, we also know that in all likelihood we could do better by fitting a linear model. So next what I'm going to do is I'm going to run a linear regression on this data and then plot the results of that regression along with a 95% confidence interval around that line. So well, I'll just do that and I'll talk about what I'm doing once it's on the screen. There we go. So what you can see I've done here is here's the part where I actually run the model. The new data equals new dat just tells it I want to predict. I want to obtain these predictions for data in the new dat data set, which is has one variable education with discrete quantities from 0 to 7. So in other words, you don't have to predict the income for every single data point in the data set. I only need to predict it for those 8 values of education that are relevant. So I'm running the linear model here, and then with the predict function, I'm getting the predictions for the appropriate values of education. And the SE fit tells me I want to actually get standard errors for each fitted value. I want to predict the standard error of the fitted value around that. So then I'm able to plot a line giving me the predicted value and 1.96 plus or minus the standard error, which is the 95% confidence interval, which you have hopefully learned in an earlier statistics course. And I'm plotting that against the Nadaraya-Watson fit. And what do we see? Well, what we see is that for the most part, the Nadaraya-Watson fit is bouncing around inside of the 95% confidence interval. There's 1 out of 8 of the predictions is outside the 95% CI. That's exactly what we'd expect from a 95% CI. 5% of the time we reject something due to random chance, and that's pretty much what we're doing here. 1 out of 8. A little more than 5%, but we only have a sample of 8, so what are you going to do? This is a good indication in this case that the linear model is probably a good choice. Our Nadaraya-Watson model is not improving very much. And you might notice that when it's a good choice, the linear model does a much better job of recovering the true DGP. Our intercept is far closer to the true value of 8,000 than the Nadaraya-Watson estimate was. And we also get less of that bouncing around that we saw in the Nadaraya-Watson model because the linear model imposes the assumption of linearity onto the data set. In other words, it assumes that that's true and then uses the data to inform exactly what line it's going to draw. So the first lesson we can learn from this little exercise is that, let me just go back to blue here, when assumptions are good, they add value to an analysis. Whoops. They allow us to extract more information. Or actually, I shouldn't really say more. They allow us to extract better information out of a data set, and they allow us to extract that information with greater confidence. And actually, that's really, I should make that item 2. Extract better information with greater confidence. When the model is good, in other words, when its assumptions are good ones, we do well by imposing those valuable assumptions on the data. Now, we can actually see the better information, the better answers by just looking at the lines. But the second bit, the extracting with greater confidence, requires a little bit more doing to show. So the way we can demonstrate that you get more confident results is by extracting the standard errors of each prediction out of both the Nadaraya-Watson model and the linear model. And in order to extract the standard errors, I'm going to have to actually run a different lowest procedure. I can't use the lowest call in R. I have to use the non-parametric or NP library in R, which I'm going to call up right now. And this allows me to run the same model that I ran before, just with using a different program that allows me to extract the standard errors. So the first call here is the call calculating the optimal bandwidth to use for the model. But previously I used a bandwidth of 25%. This procedure will actually calculate an optimal bandwidth to use. And then the next step actually runs the non-parametric regression, and you can see this actually creates a whole bunch of different outputs. If I run this separately, you'll see it spits out the optimal bandwidth, which in this case is 0.39, and I can get a lot of different things out of it. For example, I can get the fitted values. Oh, wait a minute. If I go to help np-reg, it should tell me I can get, it's mean. So I can get the fitted values for each of the points. There's my fitted values for each of the individuals in my sample data set. I can also, you'll see here, I can get the standard errors of those estimates. And so what I'm going to do is I'm going to plot the standard errors of the estimates out of this Nadaraya-Watson model against income values. So here's the observed income. Here's my standard error of the estimate. In fact, maybe I could even add in a Y label, SE of predicted income. Oh, you have to call it YLab. There we go. Doesn't want to seem to stick that in there. That's interesting. Weird. Oh well. Might be. Let's try clearing that. There we go. Oh, well, now let's put them both in. So what I've done is I'm plotting the standard error of predicted income for the black points, which are these are the points for the Nadaraya-Watson model. You can see that there are sort of discrete levels. Those correspond to the discrete levels of the predictor variable education. So if you remember drawing the line in there, there are really only 8 prediction points there. That means there are 8 standard errors. I've done the same thing in red, but I've done it using the standard errors for the linear regression model. And what you can see is that the linear regression model does produce standard errors for the fits, but they're much smaller than the standard errors produced by the Nadaraya-Watson model. And that makes sense intuitively because we've added information to the model via the assumptions of linearity, and consequently the model has more information to work with when it produces its predictions, and consequently produces predictions with greater certainty. So the linear model gives us more certainty in our predictions, which is a good thing if we have a reason to believe those predictions are accurate. And in this case, based on the fact that we know the DGP is linear and based on our visual inspection, we do have reason to believe that. So that goes back to our original point here. When the assumptions that we make in a model are good, they do add value to analysis. They allow us to extract better information with greater confidence. This advantage gets greater and greater as the number of dimensions or number of predictors, the number of dimensions in the predictor matrix, or the number of dimensions, the number of variables we're going to use to predict gets bigger. So what I'm going to do is use the scatterplot 3D library to show you another sample data set that I've created. Here, income is not only related to my education, but also to how much money my parents made. And if I run a nonlinear regression model, a non-parametric regression, a Nadaraya-Watson 0-3 regression, and then plot the standard errors of that, and I do the same thing for a linear model that I run, and here we go. Let's see, it'll just take a second to run. You'll see that we actually do even better yet. My standard errors for my Nadaraya-Watson model are considerably higher for every data point than those for my linear regression model. The red's the linear regression, the black's the Nadaraya-Watson model. So I get more accurate and equally reliable data or results from my model if I can presume that the assumptions of that model are good ones. And again, in this case, I know that they are because we have the advantage of having created them to be so that I'm certain that they are. Now, those are the advantages of using a linear model, and I'm sorry, yes, those are advantages of using an assumption-laden model, including a linear model. Just to add a bit to this lecture, these advantages grow as the number of predictor variables grows. The reason for that is that most non-parametric models, including the Nadaraya-Watson model, operate primarily by extracting information out of the data set and not adding to it via assumption. And so the more dimensions there are, the more that's being asked of the data. So here's a 2- and a 3-dimensional axis that we can use to illustrate this property. So let's start with the 2-dimensional axis here. So I'm predicting y with x, and I've got some data that I'm going to do for that, or I'm going to use for that. If I use a Nadaraya-Watson model, and let's say I want to predict y at 10 different points, 1, 2, 3, 4, 5 here, 6, 7, 8, 9, 10. I've got 10 different points that I need to calculate from the data set. But if I take that exact same data, so now I've got, I don't know, a little cloud of data in here, and I want to predict y rather, using x and z, and I want to do it for 10 points on x and z. Now I've got 10 squared, or 100 many locations at which I need to calculate a prediction. Here I had 10 locations. Here I'm going to have 100. Each, if you think of there being imaginary grid lines corresponding to the various points on this xz axis, and I'm doing a pretty poor job drawing them, but nevertheless I hope you can get it anyway. Should have drawn them in gray. Each one of those intersections is a point where I need to generate a prediction using a locally weighted average. And just think, if I've only got, say, 50 or let's say I've got 50 data points. Here, on average, if the data is spread over the x-axis pretty evenly, I should have about 5 points per location to do my calculations. Here, I've got, on average, a half of a point per location. If I had 10 to the 3, so I had x, z, and w, and now we're going to make predictions on for y using x, z, and w, I'd have 1,000 locations, and 50 divided by 1,000, we're talking about 5 over 100, or 0.05 many points per location, just a tiny number of points per location. So I'm asking for more and more information from the same data set, and I'm going to get less and less out of it. So this is called the curse of dimensionality, and that's why the advantages of parametric models grow as the number of predictor variables gets larger. On the other hand, it's certainly not the case that using assumptions in models is without its own advantage or disadvantages. And we can see that pretty clearly if we create a data set for which the linear model is a poor fit and try to fit a linear model to it anyway. So I've now created an income and education 2-dimensional data set here. And what I've done is I've made it so that there's a little bit of a sine wave here. Initial education doesn't really change income much. Then greater education increases income, and then it turns around and greater education decreases income, which is not inaccurate. This is fake data, but that's a fairly accurate depiction of movement in real data sets. Now, if I use the Nadaraya-Watson model to draw predictions, and here I'm using a span of 25% of the data, you can see that it tracks those movements pretty well. It's recapturing that sine curve pretty easily. On the other hand, if I try to slap a linear model on top of it, I get terrible results. So here, the standard errors of the OLS regression are not encompassing most of the non-parametric model's predictions, indicating, at least in my mind, that the linear model is not doing a very good job of approximating that underlying function. It's not the case that adding assumptions willy-nilly is always an unmitigated benefit. The assumptions have to be good ones that don't do abuse to the underlying DGP, in order for us to derive the benefits of greater efficiency and greater accuracy that I've ascribed to parametric models. If I wanted to get those advantages in this sort of situation, I would have to propose a parametric structure of assumptions that made sense for this data set. For example, I could apply a sine wave. I know that this data came from a sine wave, and so perhaps I could do that. If I didn't know that and I was just kind of eyeballing it, I might say that this data set kind of looks quadratic, and so I might end up putting a quadratic function on top of a sine wave. Now, whether that actually is better or worse than a non-parametric regression, it just depends. It depends on how good the how do I say this? How much abuse the assumptions do to the underlying DGP. We know that this is not a quadratic data set. If I try to use a quadratic parametric structure to approximate it, I might do better than non-parametrics, and I might do worse. It sort of just depends. In general, though, non-parametric models' main advantage is not being sensitive to this kind of assumption framework. We don't have to think about it. But if that framework is constructed well, and it's a good match to the underlying data set, we do derive benefits from it. So that's, I think, the main reason why linear modeling persists, despite the fact that it's relatively simplistic. It turns out that without a great deal of effort, we can use linear approximations to a wide variety of different data-generating processes to recover them with reasonable efficiency, and without running into the curse of dimensionality that we would inevitably encounter in a purely non-parametric framework.